Okay, so today we'll talk about forces and motion, like the title suggests. Okay. If you want to get something to move, you have to apply a force on it. Okay, and a lot of animals move, you move, and so on. Okay, so we want to understand all of that. Oops, sorry. Okay, so forces and motion. Okay. So here's a situation. So you're applying a force on the syringe. Okay. When you apply a force, there's an agent that applies a force, and there's an object on which the force is applied. Okay. So a force is a push or a pull. It's an interaction between an agent and an object. Okay. All right. So now there's something else going on here in this diagram that we want to understand. Okay. So let's say I push. Okay. So what we want to understand is this here. For instance, I push my hand with a force of 10 pounds. Does that hurt? Okay. I'm going to do the same thing here with 10 pounds. Now, does that hurt with a pointed object? Okay. That hurts. So what is the difference? I'm sorry? The relevant thing here is pressure. Okay, and we'll talk about this later. Pressure is force divided by area. Okay. So here you applied a 10-pound force, and that force is transmitted to the tip of the needle. Okay. And when that force is applied over a smaller area, a greater pressure will break your skin. Okay. All right. So in this chapter, you'll learn how to identify forces. We'll talk about various forces, and also we'll talk about something called a free body diagram. So in physics, we draw the simplest possible diagram to show what is relevant. Okay? And we'll talk about that. Okay, what does the word equilibrium mean to you guys? Anybody? What does equilibrium mean? Okay, so you can guess that equilibrium means something is at rest. Okay? So technically, equilibrium means acceleration is zero. Okay? So if you are at rest, that is called static equilibrium. Okay? And why is this relevant? When you drive your car over the bridge, do you want the bridge to move? No, of course not. Okay? So you want structures to be in static equilibrium. It turns out that if an object is moving at constant velocity, that is also an equilibrium. Okay? But oftentimes we'll be concerned with static equilibrium. Okay? So this gymnast is in equilibrium. What you'll learn, okay, so when I'm standing here, I'm in equilibrium. Okay? Why am I, if I want to be stable, what should be true? If I want to fall down, can I fall down? How do I fall down? If I lean forward, I can fall down, right? Okay, when I lean forward, what happens?
Your balance is off.
Huh?
Your balance is off.
Okay, so here's what happened. Okay. We'll learn about something called the center of gravity of a person. Okay. This is the footprint of this object right now. For this object to be balanced, the center of gravity needs to be right above the footprint. Okay, so if she wants to fall down, all she has to do is lower this leg and make the center of gravity come here outside the footprint, and she'll fall down. She wants to fall down this way, she just has to bring the center of gravity here, and she'll fall down. Okay? So again, coming back to my example, here's my footprint between my feet. Okay, as long as my center of gravity is on top of my footprint, then I'll be balanced. If I want to fall down backwards, I just bring the center of gravity outside the footprint and fall down. Okay? All right, so in this diagram, the gymnast is in equilibrium because all the forces acting on her are exactly balanced. Okay, we'll learn about torques as well. What this is saying is, okay, so what this statement is saying, her leg weight, this leg's weight is acting this way, which is trying to turn her that way about that pivot point, which is being balanced by this weight, which is trying to turn her about this point, okay? About the pivot point this way. Anyway, so as long as her center of gravity is above her footprint, she'll be balanced. So we mentioned acceleration. When you apply a force to an object, and this is Newton's second law, force is mass times acceleration. When you apply a force to an object, the object will accelerate. Okay? So these guys are applying a force to this object and it'll accelerate. So as soon as the force goes to zero, what will happen to the acceleration? If this were zero, what will happen to this? I'm sorry? It will be zero. Okay? So soon as there is no net force acting on an object, its acceleration will be zero. Okay? So a net force causes an object to accelerate. The forward acceleration of the sled requires a net force in the forward direction. If you want it to accelerate in that direction, you have to apply a force in that direction. Okay? Now this equation also tells you the following. If you want to make this bigger for a given object, what do you have to do? You have to apply a larger force. Okay? So a larger acceleration requires a larger force. And this is Newton's second law, and that's what Newton's second law states. Okay, so we'll come to that. So organisms use forces to support themselves and to move through their environment. Okay, so for instance, I'm standing on the floor here. Gravity is pulling me down. Okay, why am I not going through the earth? I'm sorry?
Because your feet and legs are applying force downwards to the floor.
Yeah, no, earth is pulling me down, so I'm pushing down on the floor, and the floor is pushing me up. Okay? Now, if I didn't have a skeleton, what would happen? If I was just a bag of water, like a water balloon.
You squish on the floor.
There you go. So I would squish on the floor. Would be my shape, right? All right. Anyway, so here's the deal, though. So my skeleton has to have certain strength to bear loads and stuff like that. But what if I lived underwater all the time? What would happen? If that's where I live.
You wouldn't need as much of a skeleton.
Yeah, there you go. Okay, so why don't you need as much of a skeleton? Why don't you need to be as strong? Okay, gravity is still pulling you down. Okay, so if my weight is 165 pounds, that's the force with which the earth pulls me down. If I lived underwater, earth would still pull me down with a force of 165 pounds. That is not going anywhere. But if you're living in a fluid, this fluid exerts a buoyant force on you. And that is almost equal to your weight. So underwater, you're weightless. Okay? Now, when you're weightless, your structures don't have to support as much weight. Okay? So if you're living underwater, you have a totally different body structure. Okay? All right. Organisms use forces to support themselves and to move through their environment. Okay. Now, so do you guys know what acceleration means? When are you accelerating? I'm sorry? Yeah, okay, so technically what acceleration means, your velocity is changing. Okay, so when you were right, when you stopped and then you start driving, you're accelerating. Okay, so you're accelerating when your velocity changes. Okay, so what this statement is saying is, force is not required to sustain a motion. If there was no friction, So for instance, if you went out in space and there was no forces acting on the object, you'd throw a ball at 90 miles an hour, a fast ball, and that ball would go forever at 90 miles an hour. Okay? So no forces are required to maintain a motion. In fact, we have a very good example of this. So here were these probes that were sent out in 1977, the Voyager probes, and they've gone out of the solar system, and there's almost zero force on them. Okay? And they're going at, I don't know, what's the speed, maybe 40 kilometers a second or something like that. Okay. So they're going from here to Palm Coast in a second. That's how fast they're going. And they'll keep going like that forever. Okay, okay, so that's Newton's first law. Newton's first law says an object that has no net force acting on it will remain at rest if it was at rest. Or if it's moving, it will continue to move in the straight line at constant speed forever, till another force comes and acts on it. Okay? All right, so, no forces are required to sustain motion. Okay? So organisms that live in environments with dissipative force but we live in an environment where there's friction all the time, so you have to, so for instance, okay, why did that stop? Friction force. Okay, so if I want to keep it moving, I have to keep applying force. Okay. So a bug underwater, a fish in water, it has to keep applying force to move. Okay, because there's a lot of friction there. Okay. So friction, such as air resistance, require organism to generate compensating force to maintain its motion. Okay. So forces needed for support. So if an organism lives in water, so for instance, I talked about the example of if I lived underwater, the forces that I would need for support would be, so if I lived underwater, there's gravity, there's the buoyant force, and these two forces almost cancel each other, so I really don't need forces to support my body. Okay? So my structure would be totally different. Okay? So we would have very different body structures than the animals that live on land. Okay? Okay, so this is a dandelion, and there are the dandelion seeds that are floating. Okay, a dandelion seed floats in the wind because of the drag forces is large enough to balance the seed's weight. Okay, so what we're saying here is, okay, if I take this keychain and drop it, it fell. Why did it fall? I'm sorry? Gravity, the force of gravity. How about this guy? Is gravity working on this guy? Yes. What happened there? Yeah, so there, well, did this guy have drag? I'm sorry?
Yes, but not as much compared to its mass.
Very good. So the drag here was negligible compared to its weight. Here, the drag is comparable to its weight. Okay? And let's say if here's an airplane. If I take this airplane and move it fast enough, you get a lift force, and if this lift force is greater than its weight, the plane would rise. Okay? So here in this guy, in the seeds here, these structures provide drag forces which are sort of canceling the weight. Okay, and so nature has designed this. Why has nature designed this? So if the drag forces cancel the weight, it can float longer, and the seeds could be spread far and wide. Okay, so nature has to consider all the forces, and That's where the design comes from, okay? So now we can answer this. So we're building towards Newton's first law. Do you need a force? Do you need to keep pushing on something to keep it going? So do I need to keep pushing on something to keep it going? If there is friction. But if there was no friction, then you don't need to. Okay? So you just push something once, and it will keep going. Okay, so let me show you a little example. Do you guys know maglev trains? Oh, here we go.
इसको बोलते हैं मैग्नेटिक लेविटेशन। जब हवा में उठने की वजह से उसको घुमाने में यूज करते हैं मैग्लेव ट्रेन। तो देख लेते इसको सुपर कंडक्टर देख लेते। जैसे गर्म होता है सिर्फ ठंडा कर लेते हैं। इसको बोलते हैं मैग्नेटिक लेविटेशन। जब हवा में उठने की वजह।
Sorry. Oh, here we go. This is the one I want. What happened? I'm sorry? Oh, there we go.
One doesn't have to be.
How many of you know of maglev trains? Where do you know? Have you been on one?
No.
Okay.
I've just seen stuff about it, like how there's one in like Japan, for example.
Okay. All right. All right. So let's get back to this. I had to keep pushing this. Why? Because of friction. What if I could get this train to float on air, and then would I have to push to get it moving? Do you see anything like this? Have you played air hockey? So what is the idea of air hockey? The puck is riding on a thin layer of air, so there's air being blown, and you dramatically reduce the friction. And then you hit the puck, it goes a long distance. It would eventually stop if you made the air hockey table from here to Boscos, you hit it, it would probably stop by the time you got to Ormond Beach. But you guys understand that? So we can do that with a train. And that's what you'll see. That's what magnetic levitation means. You put a magnet there, there'll be a magnet on the train, okay? Magnet on the track, that will float, and then all you have to do is push this train and it'll go all the way to DC. Okay? So there are functional trains like this. You can take one from Shanghai Airport to the city of Shanghai, and it's been operational for a while. Okay, so here we go.
A passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it. The The core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below minus 183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material.
So you guys saw that? No forces are needed. Well, okay, so you need a force to keep it on track. But the motion along the track, you don't need any forces for that. Okay?
That method is referred to as like quantum locking or something?
Oh, yeah. Yeah, magnetic locking. Okay. So I urge you guys to go see that video. Okay. All right, so that's what we are illustrating here. If friction could be reduced to 0, you give the sled a push, and it would go on forever. Okay. And like I said, I showed you examples of spacecraft that have been sent out, and now there's 0 force on them. And okay, so on snow, there'll be friction, and it'll eventually stop. On ice, there's less friction, so the sled would go further. And if there was no friction, it would never stop. And Mr. Galileo was the first one who sort of demonstrated this back in the 1600s. Okay, what he did was, we can't eliminate friction in everyday life. Okay? So he kept reducing friction on objects, and he eventually realized that if the friction were 0, then an object would keep moving forever. In the absence of friction, a moving sled will stay in motion without anything or anyone pushing it. Okay, and so here's again the statement of Newton's first law. An object that has no net force acting on it will remain at rest. Okay. If it's moving, it will continue to move in a straight line at constant speed. Okay. And these Voyagers, they've run out of fuel a long time ago, and they continue to move in space. In interstellar space. They've left the solar system. All right, so here's an illustration of Newton's first law. Okay. All right, so here's a car, let's say that was going at 80 miles an hour. At what speed is the dummy going at? 80 miles an hour. Okay. Now let's say the car gets stopped by a wall. Okay. Does the dummy stop immediately? No. So the dummy doesn't stop because the dummy is still going at 80 miles an hour. Why did the car stop? Because some force stopped it. Okay. Until a force stops it, the dummy will keep moving at 80 miles an hour. Okay. Now, so I'm going to just write down a couple of equations. You don't have to remember these equations. Okay, so okay, I'll tell you what these are. Again, we just want to understand what's going on. Okay, this is your initial speed. So let's say that's 80 miles an hour. This is your final speed. What is it that you want to do? You want to stop the dummy. So you want this to be 0. Okay. This is the stopping distance. This is the acceleration. Okay. Now here's the deal for your health. The larger the acceleration you undergo, the greater the forces that are acting on you, and the more damage to your body. You guys understand that? So large accelerations are not good. Okay? So I'll give you an example. So let's say I climbed the top of this building and jumped off the building, and a sidewalk stopped me. If the sidewalk stops me, it stops me over a very small, the sidewalk doesn't give. Okay. I get stopped over a very small distance. the acceleration I experience is very large, and there'll be a lot of damage. Okay? I jump off the same building, and now I put padding there. I put, let's say, 10 mattresses there. I will get stopped over a larger distance, the acceleration will be smaller, and the damage will be smaller. Okay? All right, so Newton's first law says when the car gets stopped, the dummy keeps moving, and the faster the dummy gets stopped, the smaller distance the dummy gets stopped, the greater the damage to the dummy. Okay? So if the steering wheel or the dashboard stops you, then there'll be a lot of damage to you. So how do you fix that? Airbags. Okay, that's what the airbags are about. They're stopping you over a larger distance. Okay? So that's what all safety devices are about. Yeah. Seat belts and airbags. Yeah. All right. So a force is a push or a pull, and every force has an agent. So this is the agent, and that's the object on which the force is acting. Okay? Now, the force, you see, you can push this object, harder or whatever. The force has a magnitude and direction. Okay, and when quantities have magnitude and direction, they are called vectors. They are represented by vectors. Okay, and so we want to understand that. Okay, so force can it has a direction and magnitude. Okay. Now, we'll talk about two basic classes of forces: contact forces and long-range forces. Okay. What do you think those means? Contact forces, as the name suggests, see, when the bat exerts a force on the ball, it has to be in contact with the ball. Okay. When the ball is coming from the pitcher and it's not come in contact with the bat is not exerting a force on the ball. Okay. So there are these contact forces, and here's a long-range force. Here's the Earth exerting a force on the moon. Okay, the moon is 250,000 miles away, and the Earth exerts a force on that. Okay, so these are long-range forces. Gravity, electrostatic, and magnetic forces are examples of long-range forces. You just saw an example of that in the maglev train. The train was floating over the track, and that was the track was not in contact with the train, and it was exerting an upward force. How large was the upward force when the train was on the track? How large was that force? So here's the track, here's the train, here's the force of gravity.
Equal to the force of gravity?
Very good, my friend. Equal to the force of lift was equal to the weight. Okay. All right, so forces are vectors, meaning they have magnitude and direction. Okay. Now, oftentimes we want to analyze situation, and so for instance, here's a box. This lady is pulling this box. Okay. And when we want to understand stuff, what we do is we simplify stuff. Here's the box. We represent that box as a point object here. And here's the pulling force that she's applying. Okay. And this is called a free body diagram. All right. If there's no force balancing in the opposite direction, this box will move in that direction. Okay. So now in this diagram, what we're showing is here's the box, and it's attached. A spring is attached to the box. You compress the spring. When you compress the spring, what is the spring going to do? It will push to the right, and that's what we're showing here. Okay, so this is the force that the spring is exerting when the spring was compressed. Here's a long-range force of gravity. When the box is falling down, it's falling down because the force of gravity is pulling it down. Okay. So these diagrams are called free body diagrams. Okay. What if there are multiple forces acting on an object? Okay, so here's an object. this person is pulling and this person is pulling. Okay. To calculate the effect of these forces, what you do is, so there's that force, and we've represented this box by a point. There's that force, there's this force. Okay. What you can do is add these two forces. This is the net force. And the object will move as if just this one force is acting on it. Okay. So what we're saying is, if you have two situations, okay, so there's this box again, and now I'm applying just this force on it. Okay, by looking at the motion of this object, you can't tell if there are two forces acting on it or just one force acting on it. Okay, so the effect of this guy is the same as the combined effect of these two guys. Okay. And this force is just the sum of these two forces. Okay. So it found that a single net force causes the exact same motion of the object as would the combination of original forces. Okay. And this is true no matter how many forces are acting on it. Okay. So if you have 100 forces acting on the object, all you have to do is add all the forces up, and the effect of the net force would be the same as the effect of all the forces combined. Okay, what's your weight? When you say your weight is, let's say, 150 pounds or 200 pounds or whatever, what does that mean? What does 200 pound mean? I'm sorry? That's the force with which Earth is pulling you. Okay, that's what that means. Now, we'll talk about Newton's third law in a little bit. Okay, here is this object. It's the gravitational force on this object is that. So if it's 100 pounds, it's pulling this object with a force of 100 pounds. Now, Mr. Newton tells us that this force is pulling this object with an exact equal and opposite force. So if this guy is pulling this guy with a force of 100 pounds, this guy is pulling him with a force of 100 pounds. So let's say if your weight was 165 pounds, Earth is pulling you with a force of 165 pounds. You are pulling Earth with a force of 165 pounds. Okay? So that's action and reaction are equal and opposite. You might have heard of this. But anyway, the weight force is the force with which this planet is pulling you down. Okay? So now, and which direction is the force? What is the direction of the force? I'm sorry? Yeah, down toward the center of the Earth. Okay, so you're being pulled toward the center of the Earth. So now you understand why the Australians don't fall off the Earth, because they're also being pulled toward the center of the Earth. Okay? Now, the stuff in your body, your mass, would that change if I went to the moon? Okay, so mass will not change when you go to a different planet, but the force with which it pulls you down will change. So your weight can change when you go from one planet to another. Okay, but your mass does not change. Okay, so the mass of this person is the same everywhere. Okay. Oh, I changed that should be Mars anyway. So I put a new diagram in there. Okay, so the mass of this guy is the same everywhere, but you see his weight is different. Here on Earth, it's 490 newtons. It's 2.5 times less on Mars, and much less on, it's 1/6 on the moon. Okay. So gravity is a long-range force, which is what keeps you on your chair, in your chair, keeps the planets in orbits around the sun. So here's the sun, here's the Earth. The Earth is going at 30 kilometers a second around the sun. 30 kilometers is like from here to Palm Coast in a second. Okay, and why doesn't the Earth fly off? Okay, So you guys have tied a ball to a string and whirled it around. Yeah. Now, let's suppose you whirl it around. Suppose somebody cuts the string, what will happen to the ball? It will fly away in a straight line. Okay. So there's no string tying the Earth to the sun. Okay. So it's the gravitational force that's keeping this Earth going around the sun. Okay. Okay. So gravity, a long range force, is what keeps the planets in orbit around the sun. The gravitational pull is what is called your weight. Okay. And again, why aren't you going into the Earth? The Earth is pushing you, the ground is pushing you up. With what force? An equal and opposite force. So if you're 165 pounds, the ground is pushing you up with a force of 165 pounds, and that is the weight you feel. That's your apparent weight. So for instance, you go underwater in a pool. Okay, so the Earth is still pulling you down with 165 pounds. The water exerts a buoyant force, which is 165 pounds. And now the ground doesn't have to push you up. This is your apparent weight. And so that's why you feel weightless underwater. You guys understand that? So your apparent weight is the push that the ground exerts on you. All right. On Earth, the agent is, so by the way, there is the force, the agent is the entire Earth acting on you, and the object is you. And like we said, no matter where you are located, the force on you is always directed toward the center of the Earth. Okay. Spring forces, so you've all seen springs. If you compress the spring will exert a force in that direction. And if the box is attached to the spring and you pull on the spring will pull you back. Okay. So what does the spring do? It exerts forces such that it's trying to get back to its original shape. If you compress it, it'll push you. If you stretch it, it'll pull you. Okay. And you see springs everywhere. Okay. So for instance, if I'm pushing down on this table, and I'll show you diagrams in a second, why is my hand not going through? The atoms, molecules are acting like springs, and they're pushing back on my hand. Okay. Here's a tension force. When you pull on the sled with this rope, there's a tension in the rope, and that's the tension force that's applied to the sled. Okay. The tension force can only pull. You can't push using a rope. Okay? So tension force, the way it arises, think of a rubber band. So when you're pulling on a rope, you're stretching the rope ever so slightly, and that's what's pulling it. Okay? So with a rope, you can't push. So here we'll look at tension forces. We'll look at a molecular model for it. So when you pull on this object with this rope, so what you can think of this as the following. Okay. So now I'm going to draw a bunch of atoms. So here's the rope, and you're pulling on the rope like that. Okay. So the forces between the atoms can be modeled as springs. Okay. So when you pull on the rope with a force of 100 pounds, what you're doing is you're pulling on this layer of atoms. You're pulling them away, and you're stretching these springs. Okay. And all those forces add up to 100 pounds. So you're pulling on this layer, which is pulling on this layer of atoms, which is pulling on this layer, which is eventually pulling the box. What if I increase this force to 200 pounds? What will happen? You're pulling on this thing, the spring stretches harder, longer, and all those forces add up to 200 pounds. So all this layer is pulling this layer with 200 pounds, which is pulling that layer with 200 pounds, which eventually gets transferred to the box. Okay? You let go of the force, what will happen? The spring will go back, all these springs will go back to their original shape. Okay? All right, so when you pull harder on the rope, its microscopic springs stretch a bit more, increase the spring force, they exert on the box they're attached to. Okay? The normal force, so this is the normal force, the weight of this object, the weight of the book is acting downward. Again, gravity is pulling it downward. And the table is exerting an equal and opposite force in the upward direction. And that upward force is perpendicular to the surface. And that's why it's called a normal force. Okay. And here's how it arises. So if you look at the model, so here's the book, and there are the atoms of the table. Okay. So when the book sits, these atoms, these springs get compressed, and they're pushing back. Okay. And all the little pushbacks add up to the weight of the book. Okay. It add up to the normal force. Okay. So for instance, if you sit on a bed, the spring in the mattress compress and exert an upward force on you. Stiffer the spring, the less they would compress, but the force would add up to the same thing, okay? So if you have extremely stiff springs, then the compression is very small, okay? So the book shows resting on a spring. The table may not visibly flex, okay? So when you put an object on a table, when I sit on this table, that'll flex. You can see the flex, but when this guy sits on the table, it's not flexing as much, but the atoms are compressed, okay? And so and they're pushing back on the book. We say the table exerts an upward force. We are saying the table exerts an upward force, but it's these little springs that are exerting the upward force, and all those forces are adding up to this total force. And that force is called a normal force. Okay. So an object resting on the ground compresses the molecular springs holding the ground together, and the ground pushes up on the object. So when you're standing on the ground, it's those little springs that are pushing you up. Okay. Same thing happens when you push on a wall. You're compressing those springs, and those atoms are pushing you back. Okay. This force is always perpendicular to the surface. And in mathematics, a perpendicular is also called a normal, and so that's why it's called a normal force. Okay. The force the table surface exerts is vertical, while the force the wall exerts is okay. So the direction perpendicular to so this force is always exerted in a direction perpendicular to the surface, and hence it's called the normal force. So the normal force is the force arising from the compression of molecular bonds. All right, now we'll talk about another force, friction force. Okay. So let's say if you're moving in this sled, eventually this sled will stop because of a friction force. Okay. The friction force, when the object is moving, this friction force is called a kinetic friction force. Okay, because this object is moving. Now let's look at another example. Here's a box sitting on the floor, and let's say you pull with 100-pound force in this direction. If the box didn't move, why didn't the box not move? What prevented the box from moving? This friction force prevented it from moving. And since the box is not moving, this friction force is called a static friction force. Okay, friction forces are denoted by little f, the subscript k telling you it's kinetic, and the subscript s telling you it's static friction force. Okay. Now here's the difference. This kinetic friction force, it just depends on the two surfaces. It doesn't depend on how fast the object is moving. That friction force is constant. It just depends on the weight of the object. Let's look at the static friction force. Okay, let's say I pull with a force of 50 pounds. The box didn't move. What was the static friction force? 50 pounds. I pull with a force of 100 pounds. The box didn't move. And the static friction force was 100 pounds. So the static friction force can be anywhere from 0 to a maximum value. Okay? When you apply a force greater than the maximum value, then the box starts moving. Okay? All right, so we are dealing with two kinds of friction forces, kinetic friction force and static friction force. The friction force, like the normal force, is exerted by the surface. Okay, that's because these molecules on this object and molecules on this on the surface bond temporarily, and that's what's holding it back. Okay. The difference is friction forces are parallel to the surface, and normal forces are perpendicular to the surface. Okay. Both are because of the interaction of the object and the surface. So in many cases, the surface will exert both a normal and a friction force. So this surface is exerting a friction force and a normal force. So we have two kinds of friction forces: kinetic friction forces when the object is moving, and static friction forces when the object is not moving. Okay? And the static friction force can be anywhere from 0 to a maximum value. Okay, why do we care about static friction forces? Is it useful in your life? Static friction force? Okay, so here's an example. I want to walk. How do you walk? Okay. What I'm trying to do is push my leg back. Okay. And if my leg slips, then I'm not going anywhere. Okay. So when I'm pushed back, the static friction force is, my leg is trying to go in that direction. The static friction force is preventing my leg from sliding backwards. And that is what's propelling me. Okay, so let me do a drawing here. Did you guys understand that? Okay, so let's say I'm pushing back with my legs, and the static friction force, that is the forward force that's propelling me backward. In fact, when you drive your car, so what is it that your car engine does? Okay.
Rotates the wheels.
I'm sorry?
Rotates the wheels.
Rotates the wheels. So if you guys go to a place to get your oil change, if the guy jacks up your car and turns your car on, all the wheel will do is spin. That's all that your engine can do, make the wheel spin. Now put that vehicle on the ground. That's all the engine can do. It will try and spin it. Okay? But the ground prevents this from spinning. And what is that preventing it from spinning? It's the static friction force. And so instead of spinning, the wheel rolls. And so the static friction force is what propels it. Yeah. You guys have seen drag racing? Okay, the quarter-mile drag race. Yeah. What is it that they do before they go on the run? I'm sorry? So what are they're trying to heat up the wheels so they can, the stickier the wheels get, the stronger the greater this maximum static friction force can be. Okay? So that's what they're trying to do. All right. So friction forces are very important for us. Okay. So now we'll talk about drag forces. Yeah. So friction, so a drag force is also a friction force. Okay. It's just a specialized term. We talk about friction when two solid surfaces are in contact. When an object is moving through a fluid like air or liquid, that's called a drag force. Okay. So, and again, by the way, the friction forces always act in the direction opposite to the motion of the object. So if the object is moving in this direction, the friction force was like that. When the object is moving in this direction, the friction force is like that. Okay? So friction forces always apply, they always act in the direction of, in a direction opposite to your motion. They're always slowing you down. What is it that they're doing? What do friction forces do? The energy of your motion, what happened to the energy of your motion? That's called the kinetic energy. What happened to that? What happened to that energy? Can you destroy energy?
No,
No. So what happened to that energy?
it went elsewhere.
Yeah, where did it go? That's the question. So friction forces always convert your energy into heat. Okay? So they dissipate your mechanical energy. So friction forces convert energy into heat. Okay, so, but the friction forces are always in the opposite direction. Okay, so for when an object moves through a fluid, that friction force is called a drag force. Okay. So resistive forces are experienced by objects moving through fluids, gases, and liquids. So friction forces, drag forces point opposite in the direction of motion. Okay. So drag forces can be large for objects moving through a high speed or in a dense fluid. Okay. For small particles moving in water, such as swimming paramecium, drag is the dominant force. Okay. So if you're a single-celled animal and water is where you live, okay, so drag forces are what are dominant in your life. So if you want to move from one place to another, you got to push. As soon as you stop pushing, you stop. Okay. A thrust force. Okay. So here's a rocket. There's the weight holding it down. So if it wants to lift off, it has to apply a thrust force. Okay. And this thrust force has to be greater than the weight of the rocket. Okay. Normally, if the rocket is on the launch pad, if the rocket weighs 100 pounds, the thrust force is about 170 pounds, generally for the rockets. So you lift off. And how do you get this thrust force? You have to expel exhaust gases. It's like a recoil force. Okay, you guys have, anybody shot a gun or something? Yeah. So you shoot a gun, okay. The total momentum is 0 before you shoot. When you shoot a gun, the bullet takes off in that direction and you recoil in this direction. And that's what a rocket is. So what is a rocket doing? So imagine yourself on a ice rink with skates on. You shoot a bullet, you'll go backward. If you want to go faster, what do you have to do? Keep shooting bullets. That's what a rocket is. Okay. So you expel hot gases, and the reaction force on the rocket is a push, which is the thrust force. The thrust force is in the opposite direction to which the exhaust gases are expelled. The faster you expel exhaust gases, the greater your thrust. Okay. And animals do this. Animals use this. So here is a scallop. It doesn't have fins or legs or anything. What does it do? It collects water in its chamber and shoots a jet of water. And then it'll run away from a predator. Or it can go from point A to B for better food. Okay. A squid does that. Okay. Rockets are propelled by thrust, and so are many animals. Scallops with no feet or fin They can escape predators or move to new territory by using a form of jet propulsion. A scallop forcibly ejects water from its rear, resulting in a thrust force that moves in the opposite direction. Okay. The advantage this guy has is the drag force is less. In liquids, the drag forces are large. So what does that mean if the drag forces are large? Okay, so if the friction were large, what do you have to do?
Increase the force.
You had to work harder to move. So that scallop has to spend a lot of energy to get away from its predator. But if the choice is between dying and living, right, you will spend the energy. All right, so when you apply a force on an object, what do forces do? When you apply a force on an object, we learned that this is Newton's second law. When you apply a force on an object, the object accelerates. Okay? And what this equation tells you is the larger the force you apply, the greater your acceleration. And for a given force, the more massive you are, the smaller your acceleration. Okay? So the acceleration is directly proportional to the force and inversely proportional to the mass. Greater the force, smaller the acceleration. Okay? So this is Newton's second law, F equal to ma. Okay? Okay, this diagram shows you three forces acting on this object. Okay. And what would be the direction of the acceleration? Okay, so the net force on this guy is this force plus this force plus this force. This minus this force is a force in this direction, and then this plus this. The net force will be somewhere in that direction. Okay, so the net force will be somewhere in this direction. And so the acceleration of the object is in that direction, in the direction of the net force. Okay? Okay, when you apply forces, the unit for forces are newtons. Okay, in physics, we name the units after the scientists who work in that area. Okay, so the units of forces are newtons. Mass are in kilograms, and acceleration is in meters per second. So when you apply a force of 1 Newton on 1 kg, the acceleration is 1 meters per second squared. That's what that's saying. All right, we saw that when multiple forces act on an object, all you do is add up the vectors. Force vectors. So here I'm showing you how to add vectors. If you have a vector A like this, and a vector B like that, the way to add two vectors is, what you do is you move the second vector there, and then the sum is that. Okay? So you move the tail of the second vector to the head of the first vector, and the sum is from the tail of the first vector to the head of the second vector. Okay? That's how you add vectors. And you can add vectors like that, as many vectors as you want. Okay? So the sum of A plus B plus C plus D plus E is this vector. Okay, so it's from the head of the first vector to the head of the tail of the first vector to the head of the last vector. Okay. So using that technique, you can add as many vectors as you want. Yeah. Yeah. Again, you don't have to know any of these formulas. This is just okay. So here's a vector. This is called the x component of the vector. This is the y component of the vector. Okay. So this vector is the sum of this vector plus this vector. All right, so that vector, this is the x component of the vector. I is a unit vector in that direction. J is a unit vector in this direction. Again, don't worry about it. So that's just in case you're interested. Okay. Now we talked about forces. Okay, now we'll apply to the human body. Okay, what do your muscles do? They can only contract, and they're there to apply forces to your various parts of the body. Okay, so your muscles can only contract. Okay, just like tension. Okay, when you pull on a rope, ropes can only pull, muscles can only pull. Okay, by contraction. So you have flexor and extensor muscles. Okay, what flexors do is, okay, this muscle is joined to that bone and to this bone. Okay, and you'll have joints in between. So when this compresses, it'll pull on this and it brings these bones together. Okay, so that's a flexor muscle. Well, what if you want to straighten out this leg? So now what you've done is, here's a leg, the hamstring will pull on this and bring these bones together. What if I have to stretch this leg? What I have to do is I have to use a muscle here attached to there, and that will stretch my leg. Okay? So you always have to have a pair of muscles. Okay? So this is called a flexor, and this muscle via tendons is joined to this bone, and when this compresses, it'll extend the leg. Okay? So muscles exert forces directed along their lengths by contracting. Okay, so that's all they can do. In many cases, a muscle is attached to two bones via tendons, often with a joint between the bones to allow movement. Okay? When muscles cause bones to move closer together, they're called flexor muscles. And those that cause bones to move apart, so if this leg was bent and you straighten this leg, these bones will move apart. They're called extensor muscles. Okay. So again, when this muscle contracts, this bone moves that way. Okay, so that's a flexor muscle, and this is an extensor. When this contracts, it's attached to the bone over here, the tibia over there, and the tibia moves forward. Okay. In your arms, when this contracts, this is a flexor muscle, your arm raises. Okay, and when this is attached to this bone over there, and when this muscle contracts, your arm straightens up. Okay. All right, so here's the back muscles of a person, and there are hundreds of muscles. Why do you have so many muscles?
Ranges of motion, different movements.
What's that? So you're barking up the right tree. You have lots of muscles because then you can apply a force in any direction. Okay, so now let's see this. Okay, this force is applied by that muscle contracting. Remember, muscles can only contract. This force is applied by this muscle contracting. This force is applied by this muscle contracting. Okay, so if you wanted to apply a force over here in that direction, all you want to do is just have these three forces contract. And don't use these muscles. Did you guys understand that? If you wanted to apply a force in this direction, then you got to recruit more force, more muscles. Okay? So that's why, with lots of different forces, you have a lot more flexibility. Okay? Tendons sometimes carry force exerted by a muscle to another point and may even change its direction. Okay? So for instance, in this case, you see the tendon was attached there and the force was When this muscle contracts, it's applying a forward force to to that muscle. Okay, but anyway, so you have lots of muscles, so you can apply forces in various directions and different magnitudes. This is sort of funny. You've heard of topology. Topologically, you're like a donut. You guys understand this? So, what is a donut? It's there's the body of the donut. It's got a hole here and a hole in the back. It's got one hole. That's what you have. You have a hole through your body. Okay? And of course, you can close your mouth, and the other end also you can close with something called a sphincter muscle. Okay, so you have these muscles that are circular. Okay, and when these muscles contract, they can close and open things. Okay, and these are very important. Okay, so for instance, we'll learn. So in a pipe, if you want fluid to flow, what is it? You have to put pressure different. You have to maintain a pressure difference for fluid to flow. Okay, so if you want the fluid to flow from here to there, you have to have higher pressure here and lower pressure here. Now, you learn, okay, so here's the stomach. You have lots of acid in the stomach to digest food and all that, okay? And here's the esophagus, okay? The pressure in the stomach is higher than in the esophagus. So if you lay down, what should happen? All the stuff should flow into your esophagus. That's heartburn. How do you prevent that? I'm sorry?
Lay on your side.
Have a sphincter muscle that closes the opening, okay, and preventing the liquid from flowing back. Okay. So these sphincter muscles are very important. Here's another place where you see these sphincter muscles. So, by the way, so see, this lens has something called a focal length. Does the focal length of this lens change? No, it doesn't change. It depends on the thickness and stuff. But if you want a different focal length, you can order it and it'll come to you in 3 weeks. But your eye is an amazing instrument. So I'm looking at that that vent, and I can focus there, and I'll look at him, and in a fraction of a second, the focal length of my eye lens changed to focus him. It's just like that. How did that happen? So here's what happens. Here's the lens of your eye. Your lens of the eye is suspended by a sphincter muscle, a circular muscle that can contract. When it contracts, the muscle becomes small, the circle becomes smaller. Okay? The lens is suspended by these little strings. So when that sphincter muscle contracts, these guys go slack and the lens becomes thicker. And when the lens becomes thicker, you can see close by objects. Now I want to see far off object. What do I have to do? Your sphincter muscle has to expand. These strings become taut. The lens becomes thin, and now I can focus on far off object. Just like that, in a heartbeat. All right? So these circular muscles are very important. Okay? And again, in your body, the muscles can only contract. Okay? So you use various configurations of muscles to do whatever it is that you want to do. Okay. All right, guys, so that finishes this chapter.